Hello students, we are going to discuss what is called photoelectric effect. Photoelectric effect is that one when light of suitable wavelength or frequency falls on a photometal like alkali metals, that is lithium, sodium, potassium, cesium, etc. They will release electrons and the corresponding current is called photoelectric current. The photoelectric effect has got many applications, out of which some of the common daily what we observe is this particular calculator. This is being used by many of you students for your calculations. You observe here there are solar cells, the 4 solar cells that are available here are being used by the daylight, so that it will be powered into the calculator. And we will also see some photodiodes and phototransistors. There are a number of applications of photoelectric effect in the form of photodiode. This is a photodiode, and there is a phototransistor. This is the phototransistor. A photodiode or phototransistor are made in such a way that the semiconductor is being suitably doped, so that when little amount of light falls on the particular semiconductor, either a diode or a transistor, it will be activated to produce suitable amount of current, and consequently the circuit will be either switched on or switched off depending on the need. And these are being used in making relays work. The relays will be used in making the switches off or on when the street lights are automatically switched on or switched off by these photo relays. There these diodes and transistors are being used. Earlier applications of these photo cells, this is called photoemissive cell. A photoemissive cell is that one in which the light falls on the suitable photocathode, which is silver cathode, and this is an anode. They are connected with the help of this particular battery to a galvanometer, and the circuit is complete when it is connected like this. A quartz bulb is being used. The quartz is used as that one in which ultraviolet light as well as visible light both will fall on the photocathode. So, when the light falls on the photocathode, immediately that will produce some amount of current in the form of a current observed in the galvanometer G. The photoemissive cells are some of the very early ones. They are being used in the cinematography films, where the film has got the necessary pictures, as well as on the sides of the picture the sound is being dubbed there. If a film is shown, you will be able to observe the corresponding sound intensity, the intensity variations, along with that a line, and this light from that sound intensity line falls on this photoemissive cell, that will produce the corresponding sound, that is the dialogue or a particular song, whatever it is, that will be shown in the cinema. So, they were being used in the cinematography, and we are going to use such similar photoemissive cell in one of the experiments that we are going to do now and show the necessary results. Earlier type of photo cell applications were not sufficient to increase the value of the amount of light converted to electrical energy. Hence, they used for very low amount of light applications. The applications are something similar to light from stars which fall on a telescope, and the light is being sent to, directed and focused to what are called photo multiplier tubes. So, such light when falls on a photocathode is being diverted into the direction of what is called a diode. One is a diode, one does it multiplies, it doubles the amount of light falling on it. So, here one ray is falling on that and it will become 2, and the second diode these 2 rays falling will become 4, and the third diode these 4 rays falling on this will become 8. So, in this form the diodes suitably adjusted within a photomultiplier vacuum tube will increase one particular ray falling on that into the required number of amplified values and corresponding current, and that is being fed to the necessary equipment which measures the light that is coming from stars, which give various information, something similar to the types of elements that are observed in the stars and their energy state or ionization state and various other details. So, in this way the earlier telescopic observation is being helped by the photoelectric effect, which is supported by the in the form of photomultiplier tube. This particular visual that you are observing now is a direct application of photoelectric effect in the form of what is called photoelectric motor. A light falls on this particular photocathode and it is being fed into a motor with the help of a small circuitry, and which of course include photodiodes and phototransistors, which we have already seen, and that will activate a relay which is connected to a motor. Whenever the circuit is on, the motor will be rotating. Once the motor rotates, the direction in which the panel is being observed, such things are usually used in satellites, so that the panel always sees the sun to get the maximum amount of energy. This is the actual photoemissive cell we were observing in the earlier visual chart. Now, this is made by General Electric, this is 929 number, and this has got a photocathode. This is the big plate that you are observing, a pointer is shown is the photocathode, and you observe now the photoanode. This particular rod that you are observing is the photoanode. This is the photoanode, this rod that you are observing. I will show you this in a particular different direction. You will be able to observe the photoanode now, this is the rod, and between these two these connections are being given and the suitable potential is applied and the amount of current also is being taken. This is a very early type of this valve. You can see the valve base. The physics of the photoelectric effect is as old as 1890, when our Hertz, Hallwachs, Leonard, Compton and other scientists have done the basic experiments. Using the basic experiments, Einstein has given the suitable theory which made the entire quantum concept into a totally different direction. One of the early experiments done by Hallwachs is shown in this particular chart. This is the visual in which you observe the anode as A, cathode as C, and the light falls on the cathode, and immediately the current that is released and continues the circuit, and the circuit once completes, the galvanometer will show the suitable amount of current. So, when the light falls, the cathode releases electrons and consequently the current comes, hence the current is called photoelectric current. Now, the next visual that you are observing is the apparatus arrangement in which you will be observing the investigation of the photoelectric effect. The earlier one is a very primitive one, and the later on people have improved it on that, and that is being shown in this. In this also the effect is the same, but arrangement is a little elaborate, so that experimental work more can be done using this particular one. In this, E is the photometal on which the light falls through a quartz window, and it is being collected by this, and they are connected through a DP-DT into an ammeter and a voltmeter, and particular voltage application purposes a 10 volts voltage power supply is being connected here. This shows that whatever we want to do with the help of the various factors that are affecting the photoelectric current are being observed with the help of this apparatus. For example, the photoelectric current can be increased and decreased, photo intensity can also be increased and decreased, and the voltage applied between E and C are also increased and decreased. And here this is the source where the source gives the light of suitable color or the associated frequency. Now, we will change the frequency also. Apart from that, we have a facility to change the particular metal in this, that means the photo metal also can be changed. These are the factors which are affecting the photoelectric current. This is the apparatus about which we have discussed in the earlier chart. Now, this particular housing, this is the unit in which we will be observing that particular photo emissive cell, this is housed in this, and this consists of a potential applied in the both positive direction. Both these switches, when they are in the positive direction, they will be, we will be able to apply 20 volts potential. This is the knob which makes us to vary the potential from 0 to whatever value that we require. And here is a instead of a galvanometer, we have a microammeter. This is 0.01 microamperes DC also is being measured with the help of this microammeter. This shows the current which is called photoelectric current, and this is the voltage applied is being observed in this particular panel meter, which is a voltmeter. This is the amount of voltage applied between the anode and cathode of the photo emissive cell. These are the two knobs which are being connected to the galvanometer or the ammeter, microammeter. The amount of current being very small, so we are using microamperes. Here we have got a arrangement for a bulb. This bulb, when we switch on, we will observe the bulb switches on and the amount of light is directed towards a window. This window is being observed in this particular direction. This is the window through which this light falls onto that particular photocathode. So, once it falls on the photocathode, the electrons are being emitted from that and the circuit will be completed, and we will observe the corresponding photoelectric current in this particular meter. So, this is our photoelectric current meter. We have already seen this is a window through which light is falling when we switch on the light, and this light instead of falling directly onto the window, what we will do? We will insert some filters into the window. These filters are observed in this particular visual. This visual shows 4 colored filters. One is red, another one is yellow, third one is green, the fourth one is blue. Each is different colored, and hence correspondingly the different wavelengths are being there for these filters. Once we say the wavelength, it also means the frequency of these filters are different. The frequency of red filter is low and yellow filter is high, green is still higher and blue is the highest among these 4. If we want still higher frequency, we will have to go for ultraviolet light. The arrangement for that will be totally different. In this part of the visual, we will observe as the light intensity increases, the photoelectric current increases. That means, when the light intensity is 0, that means when there is no light, the photoelectric current also will be 0. And as we increase the light intensity, what do you mean by increasing the light intensity? Instead of smaller bulb, we will use bigger bulb, like say 10 watt bulb or 15 watt bulb, 25 watt bulb, then 40 watt bulb, 60 watt bulb, 100 watt bulb. As we increase the wattage of the bulb, we are increasing the light intensity. Once we are increasing the wattage of the bulb, the photoelectric current increases. Now, I have switched on this apparatus, the light falls on this window of the photoemissive cell, and I have applied using this knob a voltage of 1 volt, and I am getting a photoelectric current. The value we will be observing. With all this is done with the help of a 40 watt bulb. I am going to use a 60 watt bulb now. The earlier bulb that we have used was 40 watt, and the corresponding reading that you have seen was around 10 point something. Now, I have inserted a 60 watt bulb, showing that the wattage of the bulb is increased, the corresponding reading in the photoelectric current also increases correspondingly. Yet another part of our the photoelectric current is being affected is by the accelerating potential. This factor is being experimentally observed in such a way that the accelerating potential can be made both positive side as well as negative side, and we can have a bulb of some intensity I1 here, and the bulb of different intensity which can be made double that of this particular thing called I2. So, with the I1 intensity bulb, we will be doing the acceleration potential. This is decreased from high value to 0, it is being constant throughout. Same case with another bulb having an intensity double that of the earlier one also gives the constant value. These constant values of I1 and I2 are called saturation currents. Once we go to 0, we will be observing the fall of the current when we make the accelerating potential in the negative side. That means, we will be reversing the acceleration potential, and consequently, we will observe this particular bulb readings will come to 0 current at a particular potential called stopping potential, and similarly the bulb of higher intensity also comes down and it decreases to the same 0 as we get the earlier one. In this particular entire case, what we have done is we are using the same photo metal as well as the same current, the same color. The same color means we will use either one red filter or a blue filter, only one particular filter. That means, for that given filter, the stopping potential will be this particular one. If we have a facility of changing the photometal from A to B, as the frequency increases, the photoelectric current increases. This particular curve shows that. That means, the particular frequency for which there is no photoelectron that is emitted, we will call this as cutoff frequency, and the associated wavelength is also called cutoff wavelength. So, the cutoff wavelength for a metal B is different for that of a metal A, and correspondingly what we observe is each metal will have its own cutoff frequencies. That means, less than that frequency there is no photoelectron released from that particular photoemissive cell. Now, in this particular part of the experiment where we have a facility to vary the frequency and we have a facility to observe the stopping potential being changed. Now, that means, we are varying the various photometals and corresponding cutoff frequencies and the corresponding stopping potentials. All these stopping potentials and their cutoff frequencies are being plotted here. This is the frequency. As the cutoff frequencies change, we will have the corresponding stopping potentials change. When we observe that this frequency changes means that corresponding energy is changing. This is being observed in such a way that this follows a straight line, and this straight line cuts the x axis here, and the extension of that on the y axis intercept is being observed as W0 divided by the corresponding frequency nu. So, this W0 is called the photoelectric work function. So, the photoelectric work function is that one which is the minimum amount of energy required for the electron to get released from that photometal. Now, in this next visual we will be observing an equation that is governing the half mv maximum square is the maximum kinetic energy. Where from we are getting this maximum kinetic energy? Because we are applying Hf, that is the amount of energy, that is the light that is falling on a photometal, and it is being observed that the part of this energy of this light is used in making the electron to come out of that metal, and that particular energy is called Hf0, that is the just sufficient energy, and the remaining, the difference between these two, the amount of energy of the electron coming out and the amount of total energy that we are observing is equal to the maximum kinetic energy. If m is the mass of that photoelectron, V maximum is the velocity of the maximum velocity of the photoelectron, we will observe this particular equation holds good, and this is equal to the value of the stopping potential that we are observing multiplied by Vs is the stopping potential, E is the charge of the electron, that is half mvx maximum square is equal to the E Vs, that is the amount of potential energy. This is the kinetic energy, this is the potential energy. Now, we will rearrange this in the next equation. E into Vs, that is the potential energy, is equal to the light energy Hf minus W0, which we have already called it as the work function. Now, we will try to find out the stopping potential in this equation. Vs is equal to H by E into F minus H by E into W0. We can compare this equation with our standard equation of a straight line, y is equal to mx minus c, where m is the slope of the equation. The slope of the equation m is equal to h by e. Now, once we are able to plot this curve, and the slope of the curve multiplied by charge of the electron will give us the Planck's constant called h. This is being done by this expression is given by Einstein with his own idea of treating the energy of the photon that is coming in the form of light particle, and this form of treatment of energy by Einstein is different from the treatment made by Max Planck, where Max Planck has utilized the quantization of the energy only at a particular place where the emission of radiation is being observed. That means, it is in the only cavity where the radiation is emitted, whereas Einstein's theory is totally different from that, in the form like that from the emission of that particular photon, it will be sustaining its own energy, and the form of the packet wise arrangement of a photon or quantization is being observed throughout the life of that photon. That means, once the photon is totally absorbed by a particular metal, that energy is utilized in making the energy of the electron of that particular metal to come out of that metal, and it will be stream of these electrons that are coming to produce the photoelectric current. So, in this respect the corresponding experimental verification is being done, has been done by a scientist called Millikan. This is the arrangement made by Millikan. His arrangement is, this entire thing is in a particular evacuated chamber. In this chamber we will be observing a cathode that is being in contact with whatever metal we want. That means, this is the K means potassium, or if it comes and contacts with this Li, that is lithium, or if it comes and contacts with this, it will be connected to that particular thing called sodium. Now, this is an evacuated chamber and the radiation falls on this particular metal, whichever we are interested in, and that is being the, once the electrons are released from these metals, it is being taken by the anode, and in the circuit we have got the galvanometer. Galvanometer shows the photoelectric current that is being adjusted in this. The suitable potentials are applied using this power supply and rheostat arrangement. Now, without taking out any of these things from the vacuum chamber, then arrangement has been made by Millikan in such a way that this drum can be rotated from outside using an electromagnet. So, this drum rotates and it is being brought a suitable photometal in the direction of the radiation that is falling on it, and this particular sharp arrangement is to clean the surface of that particular photometal. So, this is an excellent way of making arrangement in verifying Einstein's photoelectric theory, and immediately he found out the value of Planck's constant h. So, at one stroke in this experiment, Millikan has proved Einstein's theory as well as the Planck's constant also has come into this. So, with this immediately Max Planck also has been given a Nobel Prize, Einstein has been given a Nobel Prize, and correspondingly immediately afterwards and in the subsequent years Millikan richly deserved his Nobel Prize.
మన ఈ ఉన్నత విద్యా కార్యక్రమాలపై మీ సందేహాలను, సలహాలను, అభిప్రాయాలను మాకు తెలియచేయండి. చిరునామా డైరెక్టర్ ఆడియో విజువల్ ప్రొడక్షన్ అండ్ రీసెర్చ్ సెంటర్, డాక్టర్ బిఆర్ అంబేద్కర్ ఓపెన్ యూనివర్సిటీ, ప్రొఫెసర్ జి రామ్రెడ్డి మార్గ్, రోడ్ నంబర్ 46, జూబ్లీ హిల్స్, హైదరాబాద్ 500033.